Hello, class. Now I'm going to go through section 4.5 with you. It's called Locating the Zeros of a Polynomial Function. It really is similar to what we were working on in section 4.4, where we were using the P over Q method to help us find the rational zeros of a polynomial. Rational being a ratio of two numbers. So there are other zeros of a polynomial that may not be able to be expressed as rational numbers, but are still real numbers. And there's a principle called the location principle, and I want to walk you through that so that you understand the concept behind how we're going to find these other zeros. So suppose that y is a function f of x, and it represents a polynomial function with real coefficients, real being real numbers. If a and b are two numbers with f of a being negative, where x going in is a, the output is f of a, and that turns out to be negative. And if I put in b, I get out f of b, which is positive. This location principle then says that the function will have at least one real zero between a and b. So let's look at that. It says down here, I put in a and I get out f of a. And I notice down here that this is a negative value. When I'm down below the x-axis, it is negative. So f of a is coming out as a negative value. You could think of this as your like y sub 1. I put in x, I get out y. Then I go to this B location, which maybe we would think of it as putting in our x sub 2. I put in x sub 2 and I get out y sub 2. And I notice that this one is above the x-axis, which means that it is a positive output. Well, this location principle says that if I get out a negative value followed by a positive value, I will definitely have a zero because I have to cross the x-axis. If I'm going from negative down here up to positive, I have to cross over the x-axis because a function, remember, a function is continuous, meaning that we don't have to lift our pencil when we trace the graph of a continuous function. So the location principle assures us that if I have an output that's negative followed by an output that's positive, I'm definitely going to have a zero between those x locations. So here's an example of how we will use the graphing calculator to help us find those consecutive integers where the real zeros exist. So take your graphing calculator, grab that, I hope you have it handy, and you're going to, I'm just going to go back to the home screen here, you're probably in your home screen, hit your y equals key so that you can load up the function. And I've preloaded mine. I have x to the third minus 4, oh, I should get 4x in there, I guess. 4x squared minus 2x plus 8. Get that loaded. Why don't you hit your graph button just so that you can get a look at what this function is doing. If you don't have it all on your picture, maybe hit zoom and 6 and standardize that window so you get it coming out. All right, once you get that done, what we're going to do is I can look very easily to see where is this crossing the x-axis. I can see it crosses right in here, and right here. What are those consecutive integers? Well, I know that I should be crossing between -2 and -1. It looks like we're going to cross between 1 and 2, and it appears 1, 2, 3, maybe between 4 and 5, somewhere in there. Have to look at that. So grab that graphing calculator back. You still have yours. Go into your table function. And what we're going to do is search for where the values change on our y scale from being a positive to a negative. Now notice right now my table's set for tenths. If I want to change that, I'm going to hop onto a whole number right now, and I can hit the plus sign and change this so that I am counting by ones. And now I'm going 1, 2, 3, 4. So if we do a quick scan of our table here, you will notice that I am picking up between -2 and -1. A sign change is going from -12 to +5. There definitely exists a root between -2 and -1. There will also be a sign change that occurs between 1 and 2 because I notice it's going from 3 to -4. So I have another sign change that exists between 1 and 2. And then let's look at that one more time. Keep scrolling down. There's the one between 1 and 2. And I'm looking for another sign change. Here it is between 3 and 4. I notice it goes from negative to positive. That means I have another sign change, and that was between 3 and 4. So I was a bit off when I was trying to look at my graph back here. It really was between 3 and 4. So very simply, if I'm trying to find consecutive integers that sign changes exist between, it's quite easy to do it with either your table function or even just looking at the graph. One thing I wanted to mention for people that are on the 83 model, they can't hit the plus sign to change their table setting from, ones or 0.1s or 0.01 changes. You have to go to the table set function, and then you'll notice you can change your table right there to count by ones. So just wanted to make that mention, and you can start your table then wherever you want as well. Maybe I wanted to start my table back at -5, and I could do that by just keying it in there and then coming down here and doing a change of 1. So that's for the 83 model that have to do it through table set. What if we wanted to get a little bit more fine-tuned and get into the nearest tenth instead of just the consecutive integers? Well, we can do that as well very easily with the graphing calculator. Go ahead and load up your y equals with this new function. And I think I already have mine loaded. I had that first one loaded, and I'm just going to shut that one off because you can turn on and turn off functions by highlighting the equal sign. So now I've got my y sub 2 loaded in, and it looks to me like I made one mistake when I loaded this. Keying on the smartboard is never the easiest thing. So that should really be a minus sign there. And then 19x squared minus x plus 6. That should be your function. You can go ahead and hit graph once you get your function loaded and get an idea of where these sign changes are occurring. It appears that we've got a sign change, and maybe that's between -2 and -1 or -1 and 0. Over here between 0 and 1, and then maybe again between 1 and 2. If I do a zoom in, I bet I could see that just a little bit clearer, as they're all pretty tight in there. Yeah, it looks like between -1, 0, 0, 1, and 1 and 2, we should find some sign changes. So I'm going to go back into my table function, second table, and I can get a clearer look. What I'm looking for are those sign changes between negatives and positives. So I know there exists one between -1 and 0. What I want to do is get in tighter and see it to the tenths. So do a table change for the 84 models. Just hit the plus sign, and you can change your table right here. So 0.1 and hit enter, and now I get more detailed information. So what I'm looking for is where does that sign change occur? And I notice right here it was negative, here it flipped to positive wise. So my sign change for my root is located between 0.6 and 0.5. negative 0.6 and negative 0.5. Which one is it closer to? Well, I come back over and analyze the y values and try to decide which is closer to 0. And it appears to me that negative 0.5 has a closer value to 0 for y rather than the negative 2.83. That would be further away from 0. If you think about your y-axis, negative 2.8 is down there, whereas positive 0.25 was just slightly above the 0 line. So in order to be close to 0, this one would be closest at 0.25. That has a corresponding x value at negative 0.5. Okay, I know there's two others, so I'm going to go back to my calculator. I'm going to do some scrolling. I'm watching my y column until it flips to a positive, or it is positive, and it switches to a negative value. I should be getting a sign change between 0 and 1, just because when we were out at that other level, we saw that on our graph. And there it is. It's happening between 0.7 and 0.8. I'm just going to pull this table off so we can circle things. Right here, we get that sign change occurring. And where is it closer to 0? I would say at 0.7, 0.1 away rather than negative 0.8 away would be closer. So 0.7 is another root. And then there is one more, so grab that graphing calculator, keep scrolling. Now that I'm in negatives, I'm looking for it to flip back to positives. And right there, between 1.4 and 1.3, I get a sign change on my y values from going from negative to positive, so I know there exists a sign change right there. If I pull this off, we can analyze it a little closer, and right here we get that sign change. Now you have to decide which is closer to 0, 0.28 or negative 1.04. Well, this would be closer to 0, so my other 0 is x equals 1.4. And that is all the work that we're doing. Here's the homework we're going to work on Monday in class. It starts on page 240, 12 through 22, 25, 40 to 44. And what I would like to do, though, is have you come to class prepared so that you've done a little bit of this. Why don't you do problem 12? And then try to do problem 19 where you're getting closest to the nearest tenth. On 12, you were just looking for consecutive integers, so it was between x being 4 and 5. Here we want to get to the nearest tenth. Maybe it was between 0.0 and 0.1 to the nearest tenth. So that is what I'd like you to come to class with prepared. I will be looking to see that you got those problems done, and then we'll have a work day on Monday. Hope you enjoyed this and were able to get a lot out of it. Remember, you can hit pause, you can replay, all of those things that you normally can do with any video on the internet. Thanks, guys. Have a good weekend.